Today in science class, we're taking a look at lesson 3 in chapter 12, titled Doing Work with Fluids. So far, we've been studying the different types of fluid dynamics on how air and liquid types of materials move and operate. Today, we're going to learn how we can understand those dynamics, how they operate, and then apply them in different types of technology using fluid forces. Fluids at rest and fluids in motion can be made to exert force that do useful work, such as pumping water from a well, making cars stop, and carrying people long distances through the air. Pushing on a fluid. The pressure in a fluid can be increased by pushing on a fluid. This figure shows how the force exerted on a brake pedal is transmitted to a fluid. We've learned that because fluids fill their container, whether it's air or a liquid, that if you apply pressure to those items, they respond in a certain way. For example, in your brakes, there are brake lines that are attached to the brake pedal, and when you apply pressure to the brake pedal, it's actually applying pressure to the fluid that is inside of that brake line. Because you've applied pressure to one part of the fluid, it applies pressure to all parts of the fluid, and that brake line will then go to the caliper that is on the rotor inside of your tires, and it will clamp down on those rotors, which will cause your axle and your wheels to stop spinning. The harder you press down, the more that fluid is pressured, the more that brake caliper clamps down, and it slows you down faster. Now, this is a property of fluids that we're going to learn is an applied science, because we know that if you apply pressure to one part of the fluid, it applies pressure throughout. Because the fluid in the piston can't escape, it transmits force that you apply throughout the fluid. This is called Pascal's principle. Suppose you fill a plastic bottle with water. Screw the cap back on. If you poke a hole in it, obviously the water is going to come out. No matter where you poke the hole in the bottle, squeezing the bottle will cause the water to flow faster out of the hole. Before you poke that hole in the water bottle that's at home, go ahead and just squeeze a water bottle that's completely full and has the cap on it. You're going to notice that pressure is exerted all throughout the entire fluid, and the rest of the bottle kind of gets really, really hard. If you poke a hole in it, obviously you're allowing it to release that pressure in that spot. According to Pascal's principle, when a force is applied to a fluid in a closed container, like the bottle of water that's closed still, the pressure in the fluid increases everywhere by the same amount. So even if I squeeze the bottom of the water bottle, you'll notice that the top will get really, really pressurized. This sometimes happens. There's a really good idea if you're drinking a water bottle and you crumple it down, but then you want to reuse it. You fill it with water the best you can, or you blow back into the top of the water bottle and you apply force. It'll actually expand that plastic to fill it back up. Well, Pascal's principle says that when any force is applied, it will apply to the entire area to where that fluid is confined. We use this in what's called a hydraulic system. Hydraulic systems use fluid to increase an input force. The fluid enclosed in a hydraulic system transfers pressure from one piston to another. An input force that is applied to a small piston increases the pressure in the fluid. This pressure increase is transmitted throughout the fluid and acts on the large piston. Here's an example of a hydraulic system. Some people have hydraulic systems in their vehicle and can cause it to raise up and down because of the electronic controls to lift and to not lift, pushing up and down on a piston. But probably the most common way in which you'll see it used is in the form of a car lift at a car mechanic, an oil change place, a car dealership, which you can actually use a small amount of energy in the form of a piston or hydraulic system to push on a fluid inside of a set of lines, and that fluid then will push on the opposite side of a piston and pick up something that's really heavy, like in this example for a car. Because the area of the large piston is greater than the area of the small piston, the output force exerted on the large piston is greater than the input force exerted on the small piston. So you can apply a small amount of force on the small piston here, and because Pascal's principle said it's applied throughout the fluid, all of that pressure that you apply here goes to this area, and then it's multiplied by the overall area to pick up something that's really, really heavy. Increasing force. Suppose that the area of the small piston is 1 meter squared and the area of the large piston is 2 meters squared. If you push on the small piston with a force of 10 newtons, the increase in pressure at the bottom of the small piston is pressure equals force times area. So you've got 10 newtons over 1 meter, force divided by area. 10 newtons divided by 1 meter, you get 10 pascals. Well, if you increase the area, that means that you're going to be increasing the overall outward force. According to Pascal's principle, this increase in pressure is transmitted throughout the fluid. This causes the force exerted by the fluid on the larger piston to increase. The increase in force on the larger piston can be calculated by multiplying both sides of the formula by the area. So in this case, force equals pressure, which you've already exerted on the small piston, by the overall area on the larger piston, and it increases force. So pressure was force divided by area. The force that's being applied on the new calculation is actually pressure multiplied by area. So you figured out what was being input into the equation, now multiplying by the area because it's showing an increase, and you get a larger output. If the area of the larger piston increases by 5 meters, so we went from 1 to 2 and it doubled. In this case, if it went from 1 to 5, it would multiply 5 times and have a 5 times the output force. So not much pressure needs to go into the input in order to be able to pick up something a lot heavier and to do a lot more work effectively. A small force pushing down on the left piston can be made much larger by the increasing the size of the piston on the right. That increase in size increases the overall output force that you can have. Pressure in a moving fluid. What happens to the pressure if a fluid is moving, such as moving air or moving water? Take a pop can and set it on the table in front of you or on the kitchen counter. I want you to use a blow dryer, or just like this, blow really closely to the side of the can here, not actually on the can, but right here. What happens to the can? What you should see is that when you blow to the right of the can or on the side of the can here, the can moves in the direction that you are blowing. You would think that because I applied air pressure here that it would move this way, but you're doing something different getting that fluid moving. The air pressure exerted on the right side of the can where you were blowing is moving faster. So the pressure is actually less than the air pressure on the left side of the can where the air is not moving. As a result, the force exerted by the pressure on the left side of the can is greater than the force exerted on the right side. You can get the can to move in that direction. So if you have air moving here, have fluid moving here, it actually lowers the air pressure, and the can will actually slide in that direction because there's a higher air pressure here that's pushing on the outside of that can. This is called Bernoulli's principle. Bernoulli's principle states that when the speed of a fluid increases, the pressure exerted by the fluid decreases. When you blew across the side of the can, the pressure exerted by the air on the side of the can decreased because the air was moving faster than it was on the other side. Let's look at a couple other examples. Chimneys use Bernoulli's principle. In a fireplace, the hotter, less dense air above the fire is pushed upward by the cooler, dense air in the room. So the chimney has this natural convection that happens as as air heats up because of the chimney, it rises. Well, how does it go out of the chimney? Why does it go out of the chimney? Bernoulli's principle. The air outside at the top of your roof on your chimney is moving past the chimney. This lowers the air pressure above the chimney. As a result, smoke is forced up the chimney, and it will move out of the chimney and continue moving in this direction because you've got low pressure here. If something's got low pressure here, it wants to move in that direction because there's less resistance. So you've got the warm air that's picking this up, and the low pressure because of moving air outside that pushes this smoke right out of the chimney. This can also be seen in different types of natural disaster events such as hurricanes and tornadoes. In a hurricane, the high winds blowing outside the house cause the pressure outside the house to lower, to be less than the pressure inside. The difference in pressure can be large enough to cause windows to be pushed out and to shatter. When wind blows across the top of the roof of a house, pressure outside the roof decreases. If the wind outside is blowing fast enough, the outside pressure can become so low that the roof can be pushed off the house. The whole roof can be picked off the house by the high pressure of the still air inside. A lot of times this happens in the case of severe tornadoes. How do we use this Bernoulli's principle and apply it in another way that helps us to create flight? Wings in flight, producing lift. A jet engine pushes the plane forward, or a propeller pulls a plane forward. Air flows over the wings as the plane moves. Lift, what causes the plane to rise, is created by making the air flow downward. When the air is directed downward, a force is being exerted on the air molecules by the wing. According to Newton's third law of motion, for every action, there's an equal and opposite reaction. See, the shape of the wing has this kind of larger surface on the top and more of a straight line on the bottom. That causes the air to move in a different type of direction here, which creates this downward force on the wing. Well, Newton's third law says that there's an equal and opposite reaction. So if there's a downward force on the wing, there's got to be an upward force on the wing. And as that plane is moving forward, that upward force and the forward motion create what's called lift. The wing exerts a downward action force on the air, so the air must exert an upward action force on the wing. This reaction is the lift that enables paper airplanes and jet airplanes to fly. Today in science class, I want you to take advantage and try to learn a little bit about this by your own experience. There's a link that's provided on our Google Classroom page that you can click on that has designs for all different types of paper airplanes. I want you to click on one that you think would be really fun and cool to make. Make one of those and see if you can create this principle of lift by the shape and the motion that you're going to create in your paper airplane. Airplane wings. The lift on a wing depends on the amount of air that the wing deflects downward and how fast the air is moving. Lift can be increased by increasing the size of the surface area of the wing. That's why big, huge, large planes that are really, really heavy metal actually can fly, because they've got large wings that create a lot of lift by their shape and by the motion that the air has when it goes around it. A large wing is able to deflect more air downward, therefore producing lift. That's why we can have these huge planes that can pick up a ton of weight and carry a ton of people a long ways without having to deal with, well, how is it so heavy? How can it fly that it's so heavy? Well, we've got the right types of fluid dynamics and principles here that create that extra lift. Let's review quickly a couple questions from the section you can get into completing your lesson reinforcement. Question 1. What does Pascal's principle state? Pascal's principle states that when a force is applied to a fluid inside a closed container, the pressure in the fluid increases everywhere by the same amount. Who stated that when the speed of a fluid increases, its pressure decreases? Bernoulli, Newton, Pascal, or Watt? This is Bernoulli's principle. Another example of this is in the shower. If you are turning on the shower and there's water moving through the air, it actually is lowering the pressure inside of that shower area. Well, what happens then to the shower curtain? Shower curtain brushes up against your leg or pushes off to the side because there's moving air inside that area, therefore lowering the pressure, and that pressure is going to cause that to move in that way to that decreased pressure. That's Bernoulli's principle again. Question 3. An airplane wing forces air to be directed downward. Why does this cause the airplane to rise? Well, you've got this equal and opposite reaction with Newton's third law of motion that says if the wing is pushed down in the air must push up on the wing. The same force is what creates lift and causes the plane to rise. That wraps up our notes for this section. Make sure that you've completed your reading, and through your reading and your notes, you'll be able to complete your lesson reinforcement. And also, have fun completing your paper airplane challenge. Click the link, take you to the page. The designs in the extra paper are in your folder. Take a look at those designs, make your airplane, and then launch that thing. See if you can get to the application of Newton's third law to create that flight that has been utilized in science and technology for years and years and years. God's blessings.